In part 1 of this two-part introduction to the rope physics lab, we analyzed the motion of a spring mass system captured on video, and we developed a computer model to predict the motion. In that earlier work, we used one fundamental principle, Newton's second law. Today we're going to employ the second fundamental principle we know, the energy principle, to gain some additional understanding of the motion. After that, we're also going to compare, in a more quantitative manner, the predicted motion to the observed motion. Now we know we need to make a choice of system whenever we start to apply a fundamental principle. For our application of Newton's second law, our choice of system was the mass by itself. We could make the same choice for the energy principle. However, we don't need to. In fact, we're going to choose a different system here. We'll choose the system to include the spring and the earth. So with this new choice of system, the interaction between the mass and the spring and the interaction between the mass and the earth are inside the system, and both of these interactions have corresponding potential energies that we can use to describe them. So we'll use them here. So the change in the total system energy, delta E, is equal to the sum of the energy changes inside the system. The change in kinetic energy of the mass, delta K, the change in gravitational potential energy, delta U sub G, and the change in spring potential energy, delta U sub S. Here we are considering the mass of the spring to be negligible, so that there are no contributions of the spring to either kinetic energy changes or gravitational potential energy changes. Now by the energy principle, the change in total system energy must be equal to all of the energy transfers with the surroundings. However, for this choice of system, there are no interactions that transfer energy to and from the surroundings, if we neglect small effects like air resistance. The interaction of the system via the attachment point to the spring does not transfer any energy because the attachment point undergoes no displacement, therefore there is no work done, no energy transfer. As a result, the right-hand side of the energy principle here is equal to 0. Let's check to see if our computer model of the spring mass system is consistent with the energy principle by computing the energy changes delta K, delta U sub G, and delta U sub S at each iteration. This means we need to compute both the initial and final energies at each iteration. To get started, we need to compute the kinetic energy and both potential energies before the program enters the loop. Here are the lines of code that need to be edited to put these energies in correctly. We'll pause here to give you a chance to write out these energies in computer code. Here's how we do this, where we make sure we use the variables we've already defined, like ball.m for the mass of the object, to keep everything consistent. Now, once we enter the loop, we see that the initial energies are defined right away. These lines of code are correct. We don't need to change these lines, and these lines are necessary because we need to make sure we save the initial energies before we make a new motion prediction for a short time delta t later using Newton's second law. Now after we predict the new velocity and new position of the mass, we now can compute the final energies, and after that the energy changes. To do this correctly, we need to edit these lines of code. So let's pause again and see if you can do this before going on with the lecture. Here's what the code should look like, so make sure you did this properly. You should now be able to run the code and check to see that there are no errors. Now at this point we need to edit the graph so that we can plot the energies and see what's happening. To do this, look for these lines of code. Right now this code is simply plotting the y position of the mass. We can change it so that we can plot multiple quantities, here multiple energy changes, at the same time on one graph. We're going to plot delta K, the change in translational kinetic energy, delta U sub S, the change in spring potential energy, delta U sub G, the change in gravitational potential energy, and the sum of all these energy changes, which is delta E, the change in the total system energy. Here's what the revised code looks like for this. Notice we need to specify the number of plots we're putting on one graph. Here, 4 plots. In the order that we specify the quantities, we're plotting the change in kinetic energy in blue, the change in spring potential energy in red, the change in gravitational potential energy in green, and the change in the total system energy, delta E, in yellow. Let's run the program and see what this looks like. Here we see that the energy changes also oscillate. The changes in both the gravitational potential energy and the spring potential energy oscillate with the same period as the position of the mass changes. Moreover, these energy changes are roughly the same size, but are opposite in phase, meaning when the spring potential energy increases, the gravitational potential energy decreases, and vice versa. We notice too that the changes in kinetic energy are also both positive and negative. The mass gains and loses kinetic energy, with the kinetic energy change oscillating twice as fast as the potential energy changes. So all these energy changes are a little complicated, but notice what the sum of all these changes is. The yellow plot is delta E and is 0, just as we would expect based on the energy principle as we discussed earlier. Let's now turn to making a comparison between the observations and the model. To do this, we need the data we saved earlier from our tracker analysis. Remember, we stored the X position and the Y position in 2 columns in a CSV file we called springmassdata_1d.csv. Make sure this file is in the same directory along with your Python VPython program that is modeling the spring mass system. After you check that, you should locate these lines of code. There are 3 groups of lines, all of which begin with the word optional. You should uncomment these lines of code so that they look like this. What these lines do is the following. The first group of lines create a red ball to represent the observed mass. The second group of lines read the X and Y positions of the observed mass into the Python program. This is done in the same way that we read in the star position data in our earlier black hole lab. Finally, the third group of code lines updates the position of the red ball using the observed data in the display window. When you run the code, you should now see something like this, where the red ball shows where the mass was observed to be, and the blue ball shows where our computer model predicts where the mass should be. The comparison isn't too bad, although the red ball seems to be rather jumpy here. That's because the time between each observed position is 20 times longer than the time between each predicted position. We make 20 predictions before we update the new observed position. A second way we can compare is by plotting the observed Y position and the predicted Y position. Here's how we can do this. First, uncomment this line of code inside the loop. Second, make sure you comment out the line of code that plots the energies. And third, change the number of plots in the graph to 2. Run the code and you should see the predicted position in blue and the observed position in red. In this case, we see they match pretty well. After all this, we're now set to do the next lab, which will involve the same spring and mass system. However, the motion will look very different. In addition to bobbing up and down, the mass will swing back and forth. This is one step closer to the kind of motion that we see in the video of rock climbers swinging on the gigantic rope swing. The motion will look more complicated, but don't be afraid. The exact same physics principles and even the computer model we developed here can be used directly to address this new motion. So if you've worked through the example in this introduction, you've already done almost all the work for the lab. Good luck, and as always, if you have any questions or difficulties, feel free to post these on the class forum.